Let us consider a curbside pickup scenario. There is a grocery store which has an option to place pickup orders. The customers can place their orders online. The store's retail team prepares these orders. The drivers arrive at the curbside pickup location, and the delivery staff carries these orders to their respective vehicles. On the retail operations side, all the orders information is stored in a PostgreSQL database. When an order is prepared, it is marked as ready by the retail team, causing an update in the database. The orders table in the PostgreSQL database would look something like this, where we have columns for customer name, driver name, pickup vehicle plate, and the order status. The store's app is used to coordinate the pickups. Each order is assigned a pickup driver. These drivers specify the details about their vehicles on the app, and upon arrival, the drivers use the app to update their location to the curbside. The app stores this information in a separate MySQL database. Here's how the vehicles table in the MySQL DB might look like. The table can have columns like pickup vehicle plate, pickup driver name, the make, model, and color of the vehicle, and also the location. What if we wanted to build a real-time dashboard that can help the delivery staff in identifying what orders need to be carried out to their vehicles? Something that looks like this. Such a dashboard would need to display the orders that are marked as ready, and their assigned pickup drivers have arrived at the designated pickup location. This dashboard could help the delivery staff in identifying the orders that are ready to be carried out to their respective vehicles. What if we also wanted to build a dashboard to help the retail team? This dashboard could list the orders that are not ready yet, but the pickup driver has been waiting at the curbside location for an extended period of time. This could help the retail team, for example, in prioritizing their efforts on orders for which people are already waiting. How would we build such dashboards? Let us look at the building blocks needed. The high-level architecture would look something like this, where the dashboards can be built using front-end technologies like React, Vue, etc. We can have a WebSocket server using sockets.io, Pusher, or SignalR. But how do we build the backend for this? The backend must maintain a list of matched orders with their respective vehicles for the delivery dashboard. It must also maintain a list of drivers that have been waiting for an extended period of time. How do we maintain such a live result set on the backend and generate notifications when it changes? One approach could be to simply poll both databases at regular intervals. The architecture could look something like this, where we poll both databases using dedicated polling services and maintain a view on the joined data in memory or in a local cache. Next, we filter these results based on the required conditions and then send the notifications to the dashboards when the result set changes. For scenarios where we need to track time, we might need the source database to track timestamps of the changes happening in the database. For instance, for the delayed orders dashboard, the vehicles database would need to track timestamps of each update made to the vehicle location so that we can compute how long a vehicle has been waiting at the curbside. There are several good things about this approach. It is easy to implement. We can use standard database queries like SQL. We also don't need a significant amount of new infrastructure. We can just use the existing databases to maintain the live result set in memory. We also do not need to worry about the persistence of the live result set, as it can always be rebuilt using the database queries on a restart. However, there are also certain issues with this approach. Experience tells us that the polling interval is hard to tune. Smaller intervals lead to frequent polling and thereby increase the load on the databases, with many pull requests not fetching any updates at all. Longer wait intervals may reduce the responsiveness of the dashboard. Moreover, this approach does not scale well with high volumes of data. For cases like delayed orders dashboard, we also need to assume that the data has timestamps for each update. If not, this would require a schema change, which may not always be feasible. Finally, the custom query logic and the in-memory joins are not a clean, maintainable, or extensible solution for the long term. A more robust approach would be to use stream processing, where the flow could look something like this. Publish the changes happening in the database to an event stream like Kafka using tools like Debezium, and then use stream processing engines like Apache Flink to process these streams. For each of our dashboards, we can write dynamic tables in Flink SQL to specify the result set we want to monitor. Flink will then maintain an incrementally updated result set for each dashboard. The stream job will write any updates happening to the result sets to the respective result topics. For example, here we see a topic for matched orders and also a topic for delayed orders. So we would still need a backend consumer to build the initial result set for each dashboard and then subscribe to the change notification topics for each dashboard, pushing these results and notifications to the ultimate dashboards using WebSockets. This approach is much better with the following advantages. The dashboards can be near real time, as there is minimal latency between the changes happening in the databases to the dashboards getting updated. There is no additional load on the database if we are reading their change logs using things like Debezium. We can also handle a very high volume of change events with technologies like Kafka and Flink. This approach is also easy to extend to additional conditions and dashboards. Let us look at some of the issues with this approach. There is significant investment in setting up and maintaining the new moving parts. We need to make sure that the BCM is configured properly for both data sources. We need to also set up a message broker like Kafka and a stream processing engine like Flink. We also need to look at event schemas, not only for the change events coming from the databases, but also for the output notifications produced by the stream job. These are processed by the backend service in the diagram to push changes to the front-end dashboards. All these event schemas must also be versioned, possibly in a schema registry, to deal with issues of schema evolution. And the work doesn't finish with just the Flink job writing the change notifications to the Kafka topic. We must still write a backend consumer, which will consume these change notifications from the Kafka topics, make some sense of it, and then push them to the front-end dashboards. And finally, stream jobs can become really complicated really fast. Let us consider the complexity of the Flink SQL job that we would need to write if we wanted to monitor the drivers waiting for an extended period of time for their curbside pickup. First, we would need to define the orders source table to capture change data in a Kafka topic. Then, we would also define a vehicle source table, which will capture its change data in its own Kafka topic. We would need to enrich the vehicle events with the latest order status. Likewise, also enrich the order events with the latest vehicle status, and then combine all these events into a single stream. We then need to track the waiting state and the transitions. For this, we first need to identify when the waiting begins, and then when it ends. Finally, we need to create an output sync table and generate the insert and delete events for the output table using a SQL query that may look like this. All of this is really complicated. Is there an easy solution? What if I told you that without writing any code, you could get a backend that watches your data sources and pushes any relevant updates to your dashboards using WebSockets? Well, let me introduce you to Drasi. Drasi can be a drop-in solution for many situations like our example scenarios here. All you need to do is to tell Drasi about your data sources using simple YAML configs, then tell Drasi what subset of data you want to watch using graph queries, and finally tell Drasi how you would like to be notified when there is any change using another YAML config. And that's it. Let us briefly talk about the three things that Drasi needs. First is a Drasi source. This is configured using a simple YAML file that provides connection details of your data source to Drasi. Many sources are supported today, including relational databases like PostgreSQL, MySQL, and SQL Server. We also support other kinds of data sources like Dataverse, Cosmos Gremlin, and even Kubernetes. There are also SDKs available for building your own custom sources in the language of your choice. As an example, here's how a Drasi source YAML would look like. Here, we specify the database connection details and the tables that we are interested in. Next are continuous queries. Drasi queries give you the power to treat all of your data stored in different sources as a single connected graph. It allows you to query this graph using OpenCypher syntax. Your data could be living in any number of systems which are of different kinds, relational, NoSQL, or even cluster managers. You can control how Drasi joins your data coming from different sources. Here is an example query that we can use for our delivery dashboard. Here, we are trying to find out the orders that are marked as ready and for which the pickup vehicle is already at the curbside pickup stall. Another powerful capability of Drasi is the support for temporal queries. You can use Drasi's temporal functions in your queries to specify time-based conditions easily, even when the underlying data source does not have timestamps. For instance, consider the delayed orders dashboard that should display the orders for which the driver has been waiting for an extended period of time. For this, we need to find out the orders that are not ready yet, but the pickup vehicle is at the curbside location waiting for more than 10 minutes. With Drasi's temporal functions like true_for, it is easy to write the query required for our dashboard as shown right here. As you can see, we are matching the orders with their respective pickup vehicles. Then, selecting only the orders that are not ready yet, and then specifying the 10-minute wait time condition using Drasi's true_for function. This function will return true when the condition is held true for the specified amount of time. The final piece is Drasi reactions. Drasi queries maintain an incrementally updated result set. Reactions process the stream of changes happening to this result set, and, in response to the changes, Drasi reactions can perform arbitrary actions in any external systems. A simple example that is relevant for our scenario is the signal_r reaction available in Drasi. This reaction can push changes to the front-end dashboards using WebSockets. Many reactions are available today, like AWS EventBridge, Power Platform Dataverse, and signal_r. There are also SDKs available in different languages, which can make it easy for you to write your own custom reaction. Here is how simple the YAML config for setting up a signal_r reaction in Drasi looks like. Let us now jump into a step-by-step tutorial where you can play with the curbside pickup example and build powerful reactive dashboards with Drasi. This tutorial is available on our website drasi.io. You can run it in 3 environments. The first is GitHub Codespaces. You can launch a codespace by clicking on this button on the tutorial page, or you can run this on a VS Code dev container. You can also use your own Kubernetes setup. For this video, we will use VS Code dev containers. Let us start by cloning the Drasi learning repository from GitHub. Once it is cloned, open the repository in VS Code. When the project has loaded in VS Code, go to the command palette and search for the option Dev Containers, Rebuild and Reopen in the container. This will give you another pop-up with a few options. Be sure to select Curbside Pickup with Drasi. This will take a couple of minutes to start a new container which has a K3D cluster, Drasi, and a few demo databases set up for you. When the container setup completes, you should be able to see this message saying Done. You can press any key to close this terminal. Now, let us start setting up our scenario. We have the retail theme, which stores the order information in a PostgreSQL database. This dev container already has a PostgreSQL database running on a K3D cluster. It has some seed data already loaded. Let's launch a simple Python backend wrapper on this database, which will make it easy for us to simulate data updates. Let us launch the Python Fast API app on port 8004, and then we can click on this button, Open in Browser. We can see this welcome message from the API, and we can also check the Swagger for the simple API wrapper on the database. Let us launch a simple app that we can imagine is used by the retail team to manage orders. Go to the retail ops front-end directory and start the node app, and open it in the browser. Now, this can be used to simulate the retail team operations. Once they are done with an order, they can mark it as ready. They can also move the orders back to preparing state, and any new order information can be added using this form here. Now, the drivers use an app for registering their vehicles and updating their location. This app stores its data in a MySQL database. We have created a MySQL service on the K3D cluster in your dev container with some seed data. Let us start a simple Python backend app that provides us with CRUD access to that database. Go to the physical operations backend directory, install the Python dependencies. Now let's launch the backend on port 8003. Open it in the browser, and we can see the welcome message from the backend API. Let's also check the Swagger. Now we have another simple app to simulate vehicle operations. For this, go to the physical operations front-end directory, install the dependencies, and launch the app. Open it in the browser, and here we see a simple front-end that can move vehicles and update the database. We can also add new vehicles using this form. Now that we have applications to simulate the order management and vehicle management, we can start building our dashboards using Drasi. First, we need to configure Drasi sources. The sources are created using YAML files like this. As you can see, the YAMLs have connection details that help Drasi talk to the sources. This YAML is configuring a source for the PostgreSQL database that stores the orders information. We have a similar YAML to configure a source for the MySQL database that has vehicle information. Here, we are giving it the database name, the table name, and the usual connection details. Let us apply these in Drasi. Here we see that the source is listed, but not ready yet. The CLI has a convenient wait command that returns once the source is available. Looks like this one is online already. We can see that the Drasi source is available. Let us apply the second source YAML as well, and wait for it to come online. And there we are. Now we can see that both the Drasi sources are online. Next, we look at Drasi query for the delivery dashboard. Here we are trying to find the orders matched to their respective pickup vehicles such that the orders are ready and the vehicles are at the pickup location. A curious question is then, how does Drasi know how to match the orders to their vehicles? Keep in mind that the orders are stored in a PostgreSQL database, whereas the vehicle information is in a separate MySQL database. Well, in the same query YAML, we are telling Drasi on how to connect the two. Here, we are creating a synthetic join by telling Drasi that the orders have a property called plate number, which can be matched to the pickup vehicle plate number. You can read more about synthetic joins on the tutorial page on our website. More interesting is the delay dashboard query. Here, we first ask for the orders and their respective pickup vehicles. Here again, we have the synthetic join called pickup by defined in the YAML above here. Now, we are taking the orders that are not ready and taking a note of the time at which the vehicle information was changed. This will help us define the time since which the vehicle has been waiting for their order. Finally, we write a where clause that will include only those vehicles in the result set that have been waiting for 10 plus seconds. The true for function here is a Drasi temporal function, one of many, which allow you to specify time-based conditions in your Drasi queries. Check out our website for more functions supported by Drasi. Now, let us apply these two queries to Drasi. And we can see both of them are now running and ready to send updates. The final part is the Drasi reaction. For our dashboards, we want a SignalR hub reaction, which will push the updates to our dashboards using WebSockets. Here is the simple YAML that you would need to get a SignalR hub up and running with Drasi. As you can see, we've specified the queries that we are interested in. Okay, now let us apply this reaction to Drasi and wait for it to be online. And there we go. Now, we will be running our dashboards on localhost while the SignalR hub is deployed in Kubernetes. So let's forward its port to localhost. And now we are ready to launch our dashboards. For the delivery dashboard, let's go to its directory, install its dependencies, and start the app. And now we can open this in the browser. Currently, there are no matched orders, so let's go to the physical operations app and move a vehicle to the curbside zone. Now, when the order for this vehicle is marked as ready, we can see that it shows up almost instantly in our dashboard. This dashboard can inform the delivery staff to carry out an order which is ready and the driver has arrived. Let us also start the delay dashboard. Go to its directory, install the dependencies, and start the app. Open this in the browser, and here we are. Currently, no drivers are waiting. Okay, so let us have another vehicle drive up to the curbside zone. And here is the order for this vehicle, which is still not ready. And for our demo, if the order is not ready for 10 seconds, it shows up on the delay dashboard. Now, this could be used by the retail team to prioritize order number 2. For convenience, we have a simple page that loads all these apps together. So open the index.html in the root directory with live server. This opens up a single page with all 4 apps loaded together. Let us say that the retail team completes order number 1 and its driver reaches the curbside. Instantaneously, we see that the matched order shows up on the delivery dashboard. The delivery staff can now carry out this order to its vehicle. Now, let us move the other 2 vehicles also to the curbside. Remember, this is causing an update in the MySQL database under the covers. The retail team then decides to complete order number 3, updating its PostgreSQL database. And again, we have an instantaneous match showing up on the delivery dashboard. And again, we have an instantaneous match showing up on the delivery dashboard. But we also observe that the driver in the red car has been waiting for a long time. And after 10 seconds, it shows up on our delay dashboard. The retail team rushes to fulfill order number 2 and marks it ready. And voila! This order can now also be carried out to its vehicle. That completes our demo. Please feel free to play out all the different scenarios with these dashboards, and I hope you get a sense of how reactive the system is and how easy it is to build it with Drasi. Drasi is an open source project, and we would love for you to join us. Use this QR code to join our Discord channel, or feel free to check us out on GitHub. Thank you all for watching.